Yes, welcome everyone. I'm very happy to introduce Bartolomeo Stellato today for our seminar. He's assistant professor at the Princeton University. Before he did his postdoc at MIT and gained a PhD from Oxford University. And he's well known for being the developer of the OSQP solver and is in general working on data-driven optimization and computational tools for mathematical optimization, machine learning, and optimal control. He gained several awards. So just to mention one, he gained the NSF Career Award, and I'm very happy to have him here today in the Robust Optimization webinar. Please, the floor is yours.
Thank you very much, Yanis and Reza, for the invitation. I'm very happy to be here. So I am. Can you hear me and see the slides? Does that work?
Yes, yeah. Everything good.
Okay. Very good. Okay, so yeah, today I'm going to talk about some work I've been doing in my group and in collaboration also with other folks not at Princeton on the topic of learning and decision-making under uncertainty. And in particular, this work is joined with several other co-authors. In particular, most of the things that we'll talk about today will be led by my student Irina Wang, but also in collaboration with Bart van Parijs from MIT and Amit Solomon, who's a research software engineer at Princeton, and my two senior thesis students, Cole Becker from MIT and Anil Yang from Orphy, who is going to join Harvard Statistics in the fall. Okay, so now what's the main question that we're trying to answer here is that there's several applications in the real world that deal with uncertain scenarios. I mean, we can have problems in logistics, transportation, but also energy distribution and production, where there's several factors that are unknown when we make decisions, including, for example, in logistics, the typical unknown is the demand, and for energy is the load demands, but also when we're dealing with renewable energy resources, it could be the amount of energy produced by these renewable sources. And also, I would say in robotics, for example, when you have an autonomous robots or a self-driving car, there's several issues and external factors that are unknown when you commit to some decisions. And also in transportation networks, you can have major events in big cities that can really force you to completely change the plans or the routes for a specific day. So in many of these applications, we need to make the systems reliable and resilient. We need to make decisions very quickly and safely whenever anything uncertain appears. And also we need to take uncertainty into account from the very moment we're formulating these optimization problems. So in my research, in my group, we try to tackle some of these issues related to decision-making under uncertainty. We try to combine theoretical concepts from optimization, learning, and control, and develop methodologies along two mainstream lines. I mean, one is optimization under uncertainty and formulations of optimization problems from data. And the other one is optimization algorithms that need to run fast enough to be solved in real time, especially in fast applications. And by doing that, I always try to connect and develop software that can be used in various applications, from autonomous systems to finance, healthcare, and power systems. So I really try to connect always through software what we're doing with the real world. And I follow these two main areas, methodological areas that are mentioned here. Now, in today's talk, I would like to focus on the part where we model decision-making problems under uncertainty. And in particular, I would like to focus on problems that look like this. So we would like to minimize a certain objective function f that is not affected by uncertainty, subject to uncertain constraints g of x and u, where u is an uncertain parameter that we don't know. Now, satisfying this constraint is impossible if you have a problem formulated like this, because you can always very easily find a realization of you that violates the uncertain constraints. So the main idea is to actually formulate different versions of this problem in order to actually guarantee in some form that we satisfy these constraints quite often, I would say. And a very common approach, which also gives the title to the seminar series, is of course robust optimization, where the main idea is to pick an uncertainty set and ensure constraint satisfaction for every realization of the parameter u inside this set calligraphic u. So there's several, now it has been developed for quite a few years so far, robust optimization. There's several techniques to reformulate these constraints, and actually there for many functions g that are concave in u, or maximum of affine in u, or maximum of concave in u, and uncertainty sets u that could be ellipsoidal, polyhedral, or other forms, we know very well how to reformulate these constraints to remove this for all u components, and to actually get a tractable formulation. So robust optimization has these nice properties that it's really powerful and expressive, and also it leads to tractable formulations. The downside, however, is that the very hard part is to construct this uncertainty set u. So how do we build this uncertainty set based on the applications that we're interested in? Now, of course, the most naive approach could be to just look at the support of the uncertain parameter, right? If you know that, let's say you have a certain limits on the uncertain parameter, which could be the demand. If you have a demand, sometimes you know that the demand cannot be negative, so you can use that information to build your uncertainty set. However, you get uncertainty sets that are very conservative and weak. Other approaches tend to take a probabilistic view and build an uncertainty set that contains a high enough probability mass of the uncertain parameter. Now, these approaches tend to work well in some forms of the uncertain parameter. For example, if it follows a Gaussian distribution, then you can really reformulate the problem tractably. However, you don't really know the true distribution of the uncertain parameter. So instead, we try to, following the modern explosion and availability of data, we try in our work to use this information and data to actually construct uncertainty sets that have good properties. So in this talk, I would like to really use data and to show you two main techniques that could help us develop uncertainty sets in robust optimization. And the main idea is to keep formulations that are tractable, so they don't lead to an explosion of constraints that we can't deal with, and that also they leads to high performance solutions, which means that they lead to low objective values and still ensure high probability of constraint satisfaction. And the two main ideas are from, on the one hand, using clustering techniques from machine learning, and on the other hand is to use differentiable optimization, which is modern ways to use the sensitivity of the solution of the robust problem with respect to the key parameters of the robust optimization problem. So in the first part, I would like to focus on clustering. And if there's any questions from the audience, please feel free to interrupt me. Also, I'll try to keep an eye on the chat. So I'll try to keep it here so that if something happens, I'll try to answer on the fly. Okay, so let's start from clustering. Now, before we jump into the clustering part, I would like to mention the kind of probabilistic guarantees that I will enforce in this part of the talk, which is probabilistic guarantees in expectation of this form. So I would like the expectation of a certain function g of x and u to be less than or equal to 0. Now, the expectation may seem a very simplistic approach, but actually if the function g could represent a maximum of concave function, so it could encode the conditional value at risk or more complicated bounds on the true probability of constraint violations. So and I will actually show you an example with the conditional value at risk. So this, I'll just keep it in expectation for simplicity, but if this function g is the maximum of concave functions in U, it's actually it can model lots of different things beyond a mere expectation. But in this case, not just to keep things simple, we have G that is a concave function of U, and it can be anything with respect to X. Now, this expectation is hard to satisfy in general because we don't know the true distribution of U. So instead of looking at that, we have a data set of realizations of the uncertain parameter U, and we call them DI, which are all the data points I. We have capital N of them. And the probabilistic guarantees that we seek to ensure are of this kind. That are the typical data-driven or finite sample probabilistic guarantees, where we have the product distribution of the samples of the uncertain parameter. And this N samples, which are the true, come from the true distribution, will give us a data-driven solution following a procedure, which is the one that I'll talk about in a couple of slides. And then we would like the solution that we obtain to satisfy the probabilistic guarantees in expectation with high enough probability over draws of the samples. Okay, this is very common in the literature, especially whenever you're dealing with N samples. So these are the data-driven probabilistic guarantees. And now, if you have a set of data points, the most intuitive thing is to actually use the empirical probability distribution. And now the empirical distribution has been used very often lately in data-driven distributionally robust optimization frameworks. And just to give a quick summary of that, because I'm pretty sure that the audience of this seminar knows this very well, but just to describe it a little bit more, these techniques from data, they first build an empirical distribution around the samples, where every sample is assigned an equal probability mass. And then we obtain this empirical distribution P hat N. And then this is going to be the center of a ball of radius epsilon, where we assume that the true distribution lives. So this set is called ambiguity set. And it's very common in distribution robust optimization to have a set of this form. And in latest work, from many of these authors, actually, many of these authors here, one of the metrics to describe this ball is the Wasserstein distance, which has beautiful connections with optimal transport and has seen an explosion of interest lately. And I would say that this is a very powerful way to model uncertainty sets from data. And I would like to connect it with the typical robust optimization formulations. And in particular, I would like to show this connection between data-driven distribution robust optimization and classical robust optimization on this 2D axis. So here I have the conservatism on the x-axis and the computational effort on the y-axis. So I see that robust optimization, since, for example, if you have an ellipsoidal set just follows an ellipsoid, has a very low computational effort because you can reformulate these constraints very easily. However, it can lead to conservative solutions if the shape, for example, doesn't capture the true shape that is of interest to us. Now, on the other hand, distribution robust optimization, the data-driven versions, they tend to have a high computational effort because they lead to many, many constraints, and I'll show you why in a couple of slides. But they can be less conservative because they really capture the data. They're very closely data-driven, and they capture the data quite accurately. So I would like in this part of the talk to build something in between these two words using clustering technique. So what does clustering do? Clustering really, most of us know that you just take your data points, you assign them to different classes. Here, you assign them to 3 classes, you compute the cluster mean, and then you do it to minimize the sum of the distances between every point di, and it's assigned cluster centers, d bar k. And k goes from 1 to capital K. Capital K will be the total number of clusters that we have. And CK are the points the data points assigned to a specific cluster K. Now you can minimize this function in whatever technique that you want. You could use k-means clustering or even mixed integer optimization approaches. But the main point is that we will deal with the result of the clustering procedure, and we will use the cluster centers instead of the original data to build a trade-off between classical robust formulation and distributional robust formulations. And the main technique will be as follows. So the idea is to take our data, apply the clustering procedure, and then obtain an uncertainty set that is given by these k clusters and a radius epsilon. And then this uncertainty set will go into a mean robust optimization problem, and I'll explain why we call it mean robust, where that will compute a data-driven solution with the desired probabilistic guarantees. And this formulation will have two key components: a constraint function that is G bar. It's not exactly G. I'll show you why we have that G bar. And also this uncertainty set that depends on the cluster centers, and that deals with the cluster centers and not the original data. Okay, so now I would like to talk about these two kinds of sets in particular. So let's start from the uncertainty set. So now what uncertainty set do we have here? We have the uncertainty set is obtained by lifting the uncertain parameter U into a higher dimension where we replicate the dimension of U capital K times, where capital K is the number of clusters, and the V1 to Vk are the perturbations around the cluster centers. So then the set will be defined by this sum, where we sum over the clusters from K1 to capital K, and we multiply by the cluster weights. The cluster weights are the fraction of points that fall into every cluster. So the more points, the higher weight a cluster has. And then we penalize the distance between the perturbation Vk and the cluster centers d bar k. This is in your favorite norm. So we're not restricting to any norm specifically. And then this is raised to the power of p, which this power of p will correspond to the power in the Wasserstein distance. So this formulation seems quite cryptic. So let me show you a couple of examples of these sets. So the first one is when we have just one cluster. So what happens if you cluster all the points together? We have one point that is the mean of your samples. We have a radius epsilon, and this is a ball around the mean of the samples. This is a typical set, for example, in robust optimization. So then another set is, there's a question about how do you calculate the cluster centers? That's actually something that we leave the users to do. I would say what we do, for example, in the experiments will be k-means clustering, which is a very scalable procedure that works very well in practice, but you could use your favorite clustering techniques. And I'll go back to this in examples. So, okay, so now the second set is k. For example, if you have 3 clusters, and p is equal to infinity, we get this summation breaks into a maximum. And then we're allowing perturbations around every one of the cluster centers of a ball of a radius at maximum epsilon. So this is the Wasserstein infinity set, where you perturb around some data points in an independent way. So we no longer sum them. And then if you have, let's say another set is, for example, when we have k clusters that is equal to capital N, and then p is equal to 2, where 2, we have the 2 norm actually, and p is equal to 2. So in that case, what happens is that we could see this set as a ball in a very high dimension, where the center is stacking all the data points in the same long vector. And then the radius of the set is epsilon, the radius of this ball is epsilon times the square root of n. And this is the set that you obtain with the Wasserstein data-driven robust distribution robust optimization when you have n points and this p equal to 2. So you can look at various different sets with this formulation. And now if you want to go to the actual mean robust formulation, what we do is that we look at this set that I defined in the previous slide. And then the uncertain constraint is just this constraint where we take the weighted mean. That's why we call it mean robust optimization, because we take the weighted mean of the function g evaluated at the perturbations vk that is weighted by the cluster weights. So you're taking a weighted mean of the perturbations here in the set and a weighted mean of the functions there. That's why we call it mean robust optimization. And it's if you write it in this way, then you obtain pretty much a robust optimization problem where u now is the lifting of the uncertain parameter here. How do we solve this problem? We can take the typical dualization technique where we dualize the constraints. And what we obtain just from a high level is that we obtain this sum, weighted sum, where we have this parameter sk, and then every constraint for every sample is given by this form. Now, I don't want you to understand everything immediately in one slide, but these are the usual suspects in this kind of formulation. You have the conjugate function of g, negated conjugate function of g, with respect to zk, we have the cluster centers and this function that depends on the order of the Wasserstein metric. And this is the dual norm of this robust, of the distance that we're taking into account. But more than that, what I would like you to focus on is that this formulation depends on, to reformulate one uncertain constraint, you need to introduce capital K constraints, which means that this formulation tends to have many, many constraints, and it can be very expensive when K is very large. For example, where K is equal to capital N, this formulation can be very, very expensive. And this is exactly the formulation that you obtain when you formulate the problem using data-driven Wasserstein distribution and robust optimization. There's exactly that formulation for these functions. And the idea is that if you have many points, this formulation can be very expensive, especially when you have mixed integer problems. So then by varying K, however, you can save a lot of computational effort. For example, we can move between one cluster K, which means we get the typical robust optimization formulation with one ellipsoid around the mean of the samples, and capital K points where we get the distribution robust optimization formulation. And in between, by varying the number of clusters, we can trade off conservatism and computational performance, which is the nice part about this. And K will be a tuning parameter of what we care about. Now, how do we guarantee constraint satisfaction? Now, the probabilistic guarantees will be going back to the original finite sample formula. We know that if you have n samples, then, and we want to ensure 1 minus beta probability of constraint satisfaction, then if you assume, for example, that the distributions are light-tailed, then there are expressions that we can compute to compute the radius of this set, which depends on the total number of samples and beta, which is the probability, the desired probability. So that radius can be computed, and this is not our contribution. It's well known now how to do that. However, what we showed in our paper is that if we do clustering, then in order to ensure the same probabilistic guarantees, we need to increase the radius given by this older formulation by this expression here. And the nice thing is that this expression is exactly related to the clustering expression, because it's nothing else than the sum of the distance between the points and the cluster centers with the same norm as the uncertainty set raised to the power of p. So this tells you that the better you cluster, then less you need to increase the radius of this ball. Now, this, if you work with these problems, you know that these are quite conservative bounds. So in order to do better, what we looked into was also, what if we fix the radius of the set and we vary the number of data points from n to k, and we vary capital K, which is, let's look now, instead of looking at these probabilistic arguments, let's look at the worst case value of the constraint. So now epsilon is fixed, and I would like to look at the worst case value of the constraint when you have capital N samples and capital K samples. Okay, and by samples, I mean the cluster centers. And now I would like to bound the relationship between these two. And you could see that by looking at the curvature of a minus G with respect to U, for example, if it's L smooth in U, then we can sandwich together the value, worst case value with N samples and the value with K samples, which is less than the worst case value with N samples plus L divided by 2 times dk. So dk is exactly the clustering objective in the same norm as the procedure that we're looking into. And the L is the smoothness constant. So now there's 2 things important here. First is that the better you cluster, the less you increase the worst case value of the constraint. And also, if L decreases, for example, if L is equal to 0 and G is affine in U, then clustering makes no difference in the optimal value or the optimal solution. This was known in from other kinds of derivations, and here we rederive this fact by really looking at the curvature of G and connecting it to this era of clustering. But this is nice because it allows us to compute bounds, and we have also, what I'm showing here holds for concave functions of U, but you can also show bounds with maximum of concave functions of U. Okay, now let me show you one example to wrap up this first part of the talk. So let's look at a sparse portfolio optimization where we minimize the conditional value at risk of my returns. So now this is the conditional value at risk, and then we have the typical X is our portfolio investments. They sum up to 1, they're normalized. We have long-only portfolios, and then to make it more challenging, we actually add a cardinality constraint. So in this case, we have 50 stocks, 5 is the maximum cardinality of your investments, and eta, which is the tail of its conditional value at risk, is 20%. So now let's see what happens here. So if we vary the number of clusters and we look at the computational time to solve this problem, you could see that by varying epsilon, it becomes more challenging. Actually, the more you increase epsilon, the more you can increase the computation time. And in particular, between 0 and 1,000 clusters, which is 1,000 data points, it can take almost 3 orders of magnitude more. This is absolutely not surprising because we have a mixed integer optimization problem with way fewer constraints if you have fewer clusters. So of course, it takes less time. But now if you want to look at the trade-off between auto-sample objective and probability of constraint violation, you could see that with one cluster, 1 point, if you cluster everything with just one set, you could see that you get the blue line. So the trade-off is not as good as with way more clusters. But if you start having, let's say, 5 clusters, you're pretty much close to the optimal performance. And then if you have, let's say, 10 clusters, you're very, very close. And then, of course, if you have 500 or 1,000 clusters, you're pretty much at the best you could do here. But the nice thing is that you can really get very close with just 5 clusters, which we're talking about the points here, which takes way less time than using 1,000 data points. So let me just wrap up this part of the talk just to give you the final take-home message here is that the mean robust optimization is just an idea to use clustering to actually help us bridging robust and distributional robust optimization. And I would say that this is if you're using this kind of techniques, it's very important and a very low cost effort to just cluster the points before applying these techniques. And we can do it not just in a blind way, but actually by characterizing exactly the effect of clustering in terms of the curvature of G. And also we have bounds of maximum of concave functions in the paper, and we can obtain multiple orders of magnitude speedups because we're just solving simpler, more compact problems. And this is the paper, and we have also the code to reproduce these numerical examples. And I'd be happy to talk more about it. And I would say there's several different techniques, of course, that could be extended based on this. But I think the idea of using data in a savvy way goes beyond these efforts. If you think about it, we are in an era where Moore's law is ending, which means computers are not becoming faster and faster in the same way as we expected before, but the availability of data is growing at an exponential rate. So this is one of the main ways in which you could think about using data, even when we have lots of data, in a wise way and compressing it in a way that can lead with more tractable formulations. Okay, so now let me jump into the second part of the talk, which is about differentiable optimization. It's another technique to deal with these problems of building uncertainty sets. And now we will not use distribution robust optimization, just a robust optimization problem. And I will start from a news vendor problem. So now news vendor problem is a typical problem where we want to minimize the costs that incur in buying some in ordering decisions. So the ordering decisions are affected by how much we pay to order a certain set of products, and also minus how much we profit by selling these products. So K is the order prices, P is the sell prices. These are parameters that are decided by external factors that we observe, and then we make the decisions after we observe them. You could imagine that the order prices could be set by a warehouse or a supplier that gives us these products, but of course the supplier sets the price. So this is not affected at all by our decisions, but of course for different prices, we need to make different orders. And then the demand, which is this uncertain demand that here we assume to be log normal just to show things in 2D, that's something that of course limits how much we sell, because of course we cannot sell more than the demand that we observe after committing to the orders. Now to solve this problem, we could actually use robust optimization and formulate the problem where the objective is written in epigraph form, and then we have an uncertainty set where the realizations of the demand appear. Okay, and now we would like to see how different uncertainty sets affect the performance of our decisions. And let's parameterize now the sets by parameters theta, which are given by a matrix A and a vector B. And now these two sets will be given by, I will show you what happens with a mean variance set, which is the most intuitive thing you could do. You just take the empirical mean of your previous realizations of the samples, empirical covariance, and then you take the set as being an ellipsoid centered at the empirical mean with the shape given by the covariance of the data. So B mean variance and A mean variance will be given by the empirical mean and the square root of the empirical covariance. Now, let's say that now we have another uncertainty set that does not have the same shape, and actually has a different shape that I'm not writing down here, but it's given by something that doesn't need to cover as much data. And I would like to compare these two sets by varying the size of this set and looking at the trade-off between probability of constraint violation and objective value in autosample. And the idea is that the reshaped set can actually do better. For example, these are trade-off curves between the autosample objective value and for the mean variance set and the other reshaped set. And you could see that the reshaped set can do better in this case. And let's look at the shape of these two sets here. So the mean variance set has this shape, which tries to cover the data as much as we can. So the green dot is actually the empirical mean of the data points. And you could see that it's an ellipsoid that is centered at that point, and it follows the shape of the data. And it captures pretty much most of the data points when you have the autosample violation that is close to 0. The reshaped set, however, is not even centered at the mean, doesn't cover a big amount of the data points, and however, it leads to the similar or better constraint satisfaction value. So now the question is, can we find this set in a systematic way and guarantee that the target probability of constraint violation is met? So this, of course, by the way, is known that you don't need high coverage. Actually, from at the beginning of the book by the robust optimization book from 2009, there are several examples where the reshaped sets do not even need to cover any single data point. So they're even more extreme than what I'm showing you here. However, here I would like to show you a systematic way to construct this set. And I would like to use data. And of course, data-driven robust optimization has seen lots of recent progress in the last 10 or more years. You've seen techniques from hypothesis testing to quantile estimation, but also Bayesian and distributional robust optimization, including the work that I talked about in the previous part of the talk, are related to data-driven techniques to build robust optimization uncertainty sets, and also deep learning with recent techniques. Also, Yanis here. These are also ways in which uncertainty sets can be built or predicted from data. And also recently, differentiable optimization appeared also in a work by Chinreddy and Delage, where the sets are built in an end-to-end fashion. And I would say probably the last work is the one that is most closely connected to what we're doing. And I would say that the main issues with these approaches is that they suffer from one of these two issues. On the one hand, sometimes only the size of the set is tuned in order to guarantee some sort of probability of constraint violation without changing the shape. Or another major issue is that there's a big decoupling between uncertainty set construction and downstream optimization task. Except, of course, in this last work, where is I would say one of the first ones that tries to build this in an end-to-end fashion while ensuring high coverage requirements, which is something that we don't do here. So we don't look at high coverage requirements, but we do it in an end-to-end fashion, and we want to understand also the shape of the set and not only the size. And the way that I would like to do it is to use the solution of the robust optimization problem to judge how well our uncertainty set is doing. So we'll have a context parameter or a family parameter that defines every instance of this robust optimization problem, which will give us a solution that depends on theta, which is the parameters of the set, and y, which is the parameter of the optimization problem, so the family parameter. And then this will feed into a loss that we will use to reshape the uncertainty set afterwards. And the idea is to use differentiable optimization because these are ways that easily deal with this differentiation step and automatically understand the shape and the size of the set. So now let's talk a little bit more about the robust optimization problem that we're dealing with here. So this is the robust problem. So we want to minimize a certain objective subject to these uncertain constraints that depends on a parameter u that lives inside the set here for at least the problem formulation. And then every time you observe y, then you solve another robust optimization problem. And you could imagine, as in the use vendor problem, this could be the order prices that somebody has sets, and that we need to make the order based on those prices whenever these changes, somebody else changes them. And then we obtain a solution x that depends on theta, which is the parameters of the set, and y, which is this context parameter. And the idea is that now that if you want to solve a problem like this, which kind of guarantees can we ensure for these kind of formulations? So a guarantee that is a classical one whenever you have a parametric or a contextual problem is to think about conditional probabilistic guarantees, okay, where you have this distribution of u condition on y whenever y changes, and you want this to be high for every realization of y. Okay, so given y, you want to satisfy the constraints with high probability. Now, this is a very strong condition, which in order to enforce it accurately, you need you need some properties of the distributions that are hard to verify, distribution of y, I mean. And also, this condition doesn't take into account the fact that sometimes it's very rare that some values of y appear. So we don't want to satisfy this for every y in an independent way in this talk. Instead, we look at an aggregate probabilistic guarantee, which is once you fix the set, we would like that the probability whenever you vary u and y, depending on their distributions, we want that the probability that this constraint is satisfied is high enough. So what we look into here is an aggregate probabilistic guarantees over a distribution of instances. Of course, this is weaker than what's above, but it's something that takes into account also the fact that some values of y may be very rare, and it tends to work well with the examples that I show you here. Now, just to remind you, x is a function of theta and y, so x is the solution of the robust problem. That's why I wrote it in this way. And just to another clarification, y is known before we compute x. That's why x is a function of y, but u is not known before we compute x. For example, in the inventory problem, y could be the prices of what we order, and u could be the demand that is not realized before we commit to certain decisions. And now the probabilistic guarantees of this form, if you want to enforce them, they correspond to the value at risk of this function g to be less than or equal to 0. So in other words, the value at risk could be seen as this point that bounds the tail of the distribution of this function g. And however, this function is a very hard to optimize function. So instead of doing that, we will look at an upper bound, which is the conditional value at risk, which is the value at risk conditional being in this upper tail here. So this could be seen as the expectation condition on this being on this tail. And this is a nice function because we can easily turn it into a constraint in terms of an expectation of this u and y, which are parameters that enter randomly. And this conditional value at risk is also can be written as needs another variable, which is alpha, which is another variable that will be included in our training problem. And one more comment here is that instead of enforcing the conditional value at risk could be less than or equal to 0, we say less than or equal to kappa, where kappa is a slightly negative value to take into account that we have a finite sample of points instead of having the theoretical distribution readily available to us. Now we'll go back to this kappa here, but think about it as being something slightly negative. So what's the training problem here? The training problem has this form where we want to minimize the expected loss over realizations of y, which is the parametric instances of our family of problems. We want to make the objective small on average. And then we would like to enforce the conditional value at risk constraint in order to enforce probabilistic guarantees. And the decision variables of our problem are theta, which are the parameters of the uncertainty set that affects the inner robust optimization problem, where X is the solution of this robust optimization problem here, and theta are the parameters of the uncertainty set here. And so the decision variables here are theta and alpha, which is the additional variable that is needed to model the conditional value at risk. So now how do we deal with this for all condition here? As I said before, there's many ways to reformulate these constraints, and I'll show you just one example of how the learned parameters enter in the final reformulation. So for example, if you have an ellipsoidal set, then theta could be given by matrix A and vector B that are given in this form, where B is B plus A Z. So these are the parameters that we would like to learn. And if you have a linear constraints, for example, that has this form where G is equal to Y plus matrix P that multiplies U transpose X for every U that lives in the set, then the robust counterpart can be easily written as something where B and A enter as in this form. So they're multiplying in an affine way the coefficients of your problem. Okay, so these are parameter affine, which is a nice structure in many optimization problems that allows us to compute the differentiation easily. So now let me go through a little bit, one word about the algorithm that we use to train this problem. So this is not a normal training problem, it's a constrained training problem because we have this conditional value at risk constraint. And to solve it, we use a constrained nonlinear optimization technique, which is a stochastic augmented Lagrangian algorithm, where we define the augmented Lagrangian of this problem here, where f is the objective value. We have lambda that is the multiplier of this constraint that multiplies this constraint. Now this is here, if we add a slack variable s here, then we obtain this as equality, and then we can write it exactly here. So s is just a slack variable that I'm adding here. And then this is a penalty parameter that multiplies the constraint squared. So this is a typical augmented Lagrangian where we just add this quadratic term. And then augmented Lagrangian approach really computes a locally optimal solution of this problem by looking at stochastic gradients of this augmented Lagrangian form. And the idea is to tune the parameters, the multiplier and the penalty until we get to the desired solution tolerance. And the main idea is that this formulation depends on this object here, which is the Jacobian of the solution X with respect to parameter theta. So the inner problem for this part is just we assume it to be convex conic optimization problem. So we can differentiate through its solutions by writing the KKT optimality conditions and computing the gradients. This is becoming very popular lately thanks to some recent works on differentiable optimization. And the main idea is it just involves solving one linear system after we compute the solution X. So if we differentiate through this condition, then we can obtain the Jacobians, and through some extensions of the stochastic augmented Lagrangian using path differentiability and conservative Jacobians, which you will find more details in the paper, then we're able to show convergence to locally optimal solutions. So now one part before showing the last examples is what happens for auto-sample data, because everything that I'm showing here is based on an algorithm that relies on training data. So to build auto-sample probabilistic guarantees, what we do is to tune the threshold kappa that I told you a few slides ago to obey to the guarantees that we're interested in. So just from a very high level, we can pick kappa based on the optimality tolerance, the target confidence, the dimension of your solution, and the number of samples. So if you pick kappa to be slightly negative according to these quantities, then if you enforce the conditional value at risk constraint over training samples, which here I write it with a hat, which means the estimated one over training samples, then we could show that using results from tail bounds, so concentration inequalities, and upper bounding the value at risk, which is a true thing we care about with the conditional value at risk, we can obtain finite sample probabilistic guarantees where we take samples over data sets of n samples of U and j samples of Y. So then this is the guarantees that we can obtain, which is for every X that lives in the set of all possible solutions. We can obtain that using results from empirical process theory. And then the idea is that if it holds for every X that lives in this set, it holds also for the actual solutions of the robust problems, which is what we can ensure. And now, using this slightly negative kappa, we can have results that ensure auto-sample probabilistic guarantees of constraint satisfaction. So again, these are theoretical results. So from a practical point of view, this is the same as setting kappa to a slightly negative value, and always the same as we did in our examples. So now we're also building a software to do all this work, which is a package that we call LROpt. It's not ready yet, but it's still, we have coded this repository where we can easily formulate and dualize robust optimization problem, which is a complicated thing sometimes, especially when you have the sum of the maximum constraints that involve sum of maxima, which is something that we ensure to do correctly. And also we automatically tune the uncertainty sets using differentiable optimization. So for example, if you have a problem that looks like this, the idea is that you can define an ellipsoidal set that depends on your realizations of U, and then train and solve this problem by reshaping the set according to the data that you feed into this software. And it is that it builds on top of CVXPy, which is something that many people are familiar with. So now let me show you one example before concluding, which is a portfolio optimization problem where we would like to minimize the negative returns. Again, the returns are given by this by this uncertain parameter U, and then we minimize this subject to, plus the deviation between X, which is our allocations, and a reference holding. So these are reference allocations that we don't want to deviate too much from. So you could imagine being either previous allocations of the record of your holdings, and you want to penalize the trades with respect to those previous allocation, or variations with respect to target reference holdings that we don't want to vary too much from. So these are the investment decisions X, and you can write this problem as a typical robust optimization problem where we upper bound the uncertain part with this constraint. And now the parameter Y in this case will be this value of the reference holdings, that in this case, it will follow the Dirichlet distribution. Dirichlet because all the components of that distribution sum up to 1, which is the normalized holdings that we always ensure. And these are the distributions in 2D samples. Actually, what I'm going to show you here is up to, let's say, 10 stocks, just to visualize something larger than that. And I would like to tune the uncertainty sets for this problem. So let's see what happens for 10 stocks here. So we have the auto-sample objective value. This is actually the true objective, not the reformulated objective. So actually the true objective that I showed you at the top of the previous slide. This is the empirical probability of constraint violation. And this is the confidence. And this is the execution time of this problem after we perform training. Training for all these methods is about is less than an hour, I would say, to tune the set for one of these examples. But after you tune it, then the execution time is this one. So let me comment on the trade-off between objective and probability of constraint violation. LRO is our method applied to a robust optimization problem with the ellipsoidal set. This is the same where after the tuning procedure, we perform the slight tuning over the size of the set to fit the target probability of constraint violation in sample. This is the same with the mean robust optimization set, which is what I talked about in the previous part of the talk. This is the same with also this fine-tuning procedure afterwards. This is the mean variance set with the robust optimization problem where we tune only the size to have this in-sample probability of constraint violation. And this is the Wasserstein distribution robust optimization set where we do the same tuning of the size to get this in-sample probability of constraint violation. So this is the target, the variation of this set actually when we just change the size and we plot the Pareto frontiers. So the worst one is the mean variance set. Then the Wasserstein distribution robust optimization set actually does better. And then if you just tune the robust optimization set by varying the shape, we can do much better by having a proper shape that is tuned exactly to this problem class. And then we do the same also for the mean robust optimization problem where we have 3 clusters here. So in this case, 3 clusters doesn't really help that much, and the performance of these 2 reshaping approaches perform similarly. But the nice thing is that not only these Pareto curves tend to be better, but actually the execution time after solving the problem can be significantly different. So the robust optimization problem, now this is admittedly a small problem, but it tends to work well. So the robust problem tends to be very fast after you training, and also the mean variance set, because it's still the same problem in terms of dimensions. However, the mean robust problem has more clusters. So again, it takes almost an order of magnitude more to solve. However, the Wasserstein distribution robust optimization problem can take significantly longer than the robust problem. So again, having a better shape sometimes gives you similar or better performance than a Wasserstein distribution robust formulation that takes much longer to solve. And again, these are smaller problems, but I would say this already gives the idea of what's going on here. So let me show you also in this example, you could see that the portfolio weights by varying the target probability of constraint violation are different. These are 10 stocks, so we can visualize all of them. And you could see that the learned versions understand, for example, in this case, that the orange stock can give potentially high returns. And you start investing here, ensuring that the probability of constraint violation is small already for these two learned sets. However, for example, the mean variance set understands that you want to invest in the orange stock only when you give up to having very high probability of constraint violation. And also the Wasserstein arrow starts here with the orange investments, but it really takes more to actually realize that you need to invest there. And by the way, these colors define the average returns, not the risk. I'm not visualizing the risk, but the average returns of each one of these stocks. Okay, so let me now wrap up this last part. So what I talked about here in the second part is to really to think about a way to learn both the shape and the size of the uncertainty sets at the same time. We wrote a bi-level optimization formulation where we use the conditional value at risk as a constraint to ensure one form of probabilistic guarantees. Again, this method, I believe it could be applied to various different forms of probabilistic guarantees. Here we enforce the conditional value at risk. We use differentiable optimization to understand the derivatives of the solution of the robust problem with respect to its key parameters. And we ensured out-of-sample probabilistic guarantees of constraint satisfaction. And the main thing that I think is quite interesting is that a simple robust optimization set with the right shape can improve much more over the standard robust optimization set and also the distribution and robust optimization formulations. So this is the paper, and also here we have the examples to reproduce them. And where again, this part relies on the software that we're building, but of course we're waiting to release a proper version of the software where we will have a separate paper on that. So now, just before concluding, I would like to mention one shameless advertisement. So we are having a workshop at the end of June in Princeton. This is a workshop on similar topics on combining learning and optimization. And it's called Workshop on Learning, Optimization, and Control. We will have exciting speakers from several different universities, and also we will be sponsored by NSF, various departments and centers at Princeton, and also IBM and Gurobi. So the website of the workshop is here, stellato.io/OLC. Unfortunately, this was even more popular than what I imagined. So we already reached the capacity of the workshop, but we're working towards having for sure recordings of the event and possibly a live streaming. So I would like to invite you, even if you can't attend in person, to actually sign up or try to connect to see the event and the talks, because I'm sure there will be great speaker and great talks. So now let me just wrap up with one main message to connect these two areas that I was talking about. So machine learning is a tool that can clearly help us formulate optimization problems. So it's not only a tool for predicting or pattern recognition in general, it actually can help us formulate problem. And I believe that instead of having problem formulations that are building offline without connecting them to the consequences of the action that they lead to, what I will see robust optimization becoming late in the next years is a training and validation procedure that is automated in a similar way as we build predictors in machine learning, where we will have an offline procedure where we tune the set and we train it. And it can be expensive. It can be more expensive than what we thought of, but it's something that can be performed offline with tailored techniques. And then we will have ways to validate and certify the resulting solutions, and then deploy these algorithms and solutions in the real world after this expensive procedure is performed offline. And with that, that's it. And I would like to thank you for your attention, and I'll be happy to answer any questions.